Welcome everyone. In this video I'm going to work a problem involving the thermal resistance concept for a cylinder. Okay? So you guys look down at the paper and we will get started. Okay, this will be 17-68. Okay, so what we have given here is steam in a pipe. The temperature on the inside, infinity, that'd be the temperature of the steam, is given. That's 320 Celsius. The conductivity of the pipe is also given, 15 watts per meter Celsius. The inside diameter of the pipe is 0.05 meters. The outside diameter of the pipe .055 meters. The thickness of the insulation I'm just going to call it IT for insulation thickness, is equal to 0.17 meters. The conductivity of the insulation, we'll call this K sub I, is equal to 0.038 watts per meter Celsius. The convection coefficient on the outside is given, and that's 15 watts per meter squared Celsius. The convection coefficient on the inside is 80. Watts per meter squared Celsius. So this is all the information that's given. Okay? And if we look at a schematic of the problem, here again we're talking about a pipe. And this pipe is covered by insulation. And this is the pipe, this is the insulation. If you take this information up here, the ID of the pipe, the OD of the pipe, and the insulation thickness, what you can see is that the radius to the inside of the pipe, if you crunch those numbers out, that comes to 0.025 meters. The radius to the outside of the pipe comes to 0.0275. Okay, and then the radius to the outside of the insulation comes to 0.1975 meters. Okay, and I'm going to arbitrarily call this one here R on the inside. I'm going to call this radius here R1, and we'll call this one here R on the outside. Okay. Of course, the temperature here will be T on the inside, T1, and then R on the outside. Okay. So you kind of see what we're doing there. And far away from the surface, we'd have T infinity on the outside, and far away from the inside of the surface, we'd have T infinity on the inside. Okay, so this is everything that's given. This is what our picture looks like. So the question is, find part A is to find Q dot, and that's per unit length. See here, per unit length, or in other words, per meter. Okay. Part B is to find the delta T, the temperature drop across the pipe. And part C is to find the delta T, the temperature drop across the insulation. See? Okay? So everything's given. This is what we're asked to find. So here again, what we want to do, solution. What we want to do, use on this is the thermal resistance concept. Okay? So if you look back at our geometry here, if you look at our picture here, our schematic, let me redraw this pipe, maybe just a quarter section of it. So if this is the very inside, okay, so what we'd have is R on the inside, R1, and R on the outside. And here again, this is our pipe, this is our insulation. Maybe have some air out here, and we have steam on the inside. Okay? So when you look at this picture, and here's the center of the pipe, how many resistors will we have? Okay? Well, alright, let's look at it. We'll have resistance due to convection on the inside, resistance due to conduction through the pipe, a resistance due to conduction through the insulation, and one more, a resistance due to convection on the outside. Okay? So here again, what we have is all these resistors in series, and since they are in series, we can just add them up. Okay, this is R convection on the inside, R conduction, I'll just say P for pipe, R conduction, I for insulation, R convection on the outside. Okay, so if you recall from our previous lecture, let me put this on another page here. Our convection on the inside is equal to 1 over H on the inside, A on the inside. So what we have here is 1 over H on the inside, the area on the inside, which is 2 pi Ri, times the length L, which of course is going to be 1 meter. All this stuff here is given in the problem. If you put the numbers in there, crunch it out, what you will see is that the value is 0.07958. And that is Celsius per watts. Okay? So our conduction in the pipe is equal to the natural log. Now you always go R on the outside divided by R on the inside. So what that means is for the pipe, it's going to be this resistance, this radius, which we, hang on just a minute, that radius there, we call that R1. Okay, so it's going to be 0.0275. So radius on the outside divided by radius on the inside, which is 0.025. So here again we got R1 divided by Ri. and then divide it by 2 pi LK. If you substitute into here, crunch these numbers out, you get 0.001011 Celsius per watts. Then we have R conduction on the insulation to worry about, and that would be here again, natural log of, we call this one R on the outside, divided by R1 is what we called it, divided by 2 pi LK. Now that's K of the insulation, and this one up here is K of the pipe. So, you know, you got two different materials, so obviously you're going to have two different conductivities. So you plug into there and you're going to get 8.257 Celsius per watt. And then R, convection on the outside again, is 1 over H on the outside, 2 pi R on the outside L. If you put your numbers in there and crunch that out, you'll get 0.05372 Celsius per watts. Now if you look at the resistance of all these, notice the resistance of the pipe, of the insulation, the thermal resistance, is orders of magnitude higher than the pipe. And typically in this situation we can just neglect the resistance due to the pipe because it's so small. But for purposes of the illustration we'll include it here. So you can get your R equivalent by adding all these up, and that will come to 8.391 Celsius per watts. And then here again we can calculate Q dot, which will be equal to T on the inside infinity minus T on the outside infinity divided by the resistance, R equivalent. And our total Q dot is 37.54 watts. Now that's per meter of pipe. Okay? So there you go. Now part B says, what is the delta T across the pipe? Well, we can use this same formula here, but only go across the pipe. So what we'd have then, here again, this is part B, and Q dot is equal to delta T across the pipe divided by the resistance from the pipe, and this is Q dot. We already know Q dot. We've already calculated resistance of the pipe. You can use those things to get delta T across the pipe. And just as we would expect, it would be very low. And doing that same trick for delta T of the insulation, we got Q dot is equal to delta T from the insulation divided by R of the insulation. Put your numbers in there and crunch that out, and you'll get 310 Celsius. Okay? Now notice Q dot, here again, it's a steady problem. So Q dot, all the Q dots are the same. Whatever goes into the pipe has to go into the insulation and out to the environment, Q dot. So all these Q dots are the same here. They're in series. Okay? So that is an example of the thermal resistance technique for a cylinder. That problem there was for a pipe carrying steam. As you saw, the delta T across the pipe was pretty much insignificant compared to the insulation. And I will see you guys next time.